Okay, hi everyone. So this video is just going to talk about chapter 4 of the notes. It's essentially how to model using difference equations as opposed to differential equations. And so the kind of key difference between differential equations and difference equations is that there's a discrete or a jump in the measurement of either time or in whatever we're measuring. So it could be people, it could be bacteria, it could be basically anything we're trying to model. But the typical indicator is if we're trying to determine the population, say at time n plus 1, then we would say that the population in the next time interval, could be next week or next year, is proportional in some way to the population now. And so this n indicates that the time or the temporal aspect, or how frequently we're measuring this, is discrete. Okay, so the notes give a few examples which you're welcome to read through. Some interesting ones there, from genetics to probability theory, lots of population stuff, and also some applications in economics and finance. So the first model says, consider a population for which the increase over any time interval is proportional to its size at the start of the interval. And that's kind of what I've written down already. So we've said that the increase in population size, so the initial, so it says consider a population for which the increase over any time interval is proportional to the size at the start of the interval. So at the start of the interval, the population size is xn, and the increase is going to be how much it goes from xn plus 1 to xn. Okay, so the increase so say it goes from 100 to 110, the increase is then going to be 10. So we're going to say that the increase, the difference between the current population size and the population size in the next time interval, must be proportional alpha xn. So it must be proportional to what the current population size. And we can obviously take this across, sum this up, and we get xn plus 1 into 1 plus alpha xn. Okay? So you'll see in a lot of these cases this term here comes about. So we often have something in the form of xn plus 1 is equal to xn. So we're saying the population of the next time step is equal to the population of the current time step plus or minus whatever else happens. So maybe some antelope are born, maybe some of them die, maybe some of them hunted, maybe they move into a different age group, that kind of thing. So basically the general form is always going to be this. And if we look at the Taylor expansion, t plus delta t, so if we Taylor expand a continuous function x around delta t, we're going to get x of t plus delta t x prime of t plus the rest of the series. And if we make this thing here the subject of the formula, we get x prime of t is equal to xt plus delta t minus xt all divided by delta t. And this difference here is very similar to this difference. So if we take delta t to be 1, so our time interval dt to be 1, so 1 day or 1 hour or 1 month, we can represent this as being, so we can say that x prime t is approximately equal to x at t plus 1 minus x at t divided by 1. So this thing here, this xn plus 1 minus xn, is really approximating the differential that we saw. So it's a discretization of the differential operator. Okay. Okay, so I think if you follow the note solutions on Sakai, you can see how the different behaviors change. So for different values of alpha or k in the notes, you can see how that affects the different behaviors. So, model 2, consider a population for which the increase over any time interval is proportional to the increase over the previous time interval. So we're going to say that xn plus 1 minus xn, so the increase in this time interval is proportional, and this time I'll use k, proportional to the increase over the previous time interval. Okay? And what we have here is xn plus 1 minus 1 plus k xn, so bringing this term over, plus xn minus 1 equals 0. Okay? And we can see that it's second order, so the difference between the highest and the lowest orders is 2, so it's a second order difference equation. And and we can solve it using techniques that we did before. So once more, the difference in the next time interval is proportional, so this constant proportionality k, I was writing to k here, proportional to the increase over the previous time interval, so going from n minus 1 to n, going from n to n plus 1 is proportional from going from n minus 1 to n. Okay. And once again, you can go through in the notes and see. So at the beginning of this chapter, we do discuss it. Sorry. Okay, so model 2, so you can see that's the behavior for different values of k. And so for some values, the population is just going to increase. So getting bigger and bigger and bigger. And then this other critical value of k, we're going to get this linear behavior in the purple line. And then for some values of k, we're going to get these stable behaviors, so the red, the green, and the orange. And then for some values of k, we get this oscillatory behavior. So the point that we're illustrating here is that from a very simple equation, we get quite a broad range of dynamics in the equation. Okay. So, there's a few exercises for you to do in the notes on the next page, so I encourage you to do that. Find the critical values for the k's and plot some of the solutions and see what they look like. So the next problem says, in a species of animal, a constant fraction of the population of alpha are born each breeding season and a constant fraction die. Okay, so we say we're trying to model some population of animal, and we say that the number of animals at the next, say, breeding season or year or month is going to be equal to how many animal we have in the beginning of the year. So the number of animal we have next year is going to be the number of animals we have this year, plus however many are born, right? So alpha is the breeding rate, so alpha times xn is going to be the number of animal that are born, and then we're going to subtract off minus beta xn. So beta xn is going to be the proportion of animal that die off. So the death rate would then be beta xn. Okay, and we can obviously group this together. So I'm going to keep this term here out, and we have xn into alpha minus beta. Okay, and we can see that if alpha minus beta is positive, we're going to be constantly adding animals to this population. Okay, so if the birth rate is higher than the death rate, then obviously our population is going to grow because more animals are being born than that are dying in a season. If beta, the other way around, if beta is bigger than alpha, then this term here is going to be negative, and we're going to be subtracting off more than we have. Well, we're going to be subtracting off. We're going to be losing animals in each season. So if the death rate is higher than the birth rate, then the population will be decreasing. More animals will be dying than are being born, and then obviously the population die off. And there's a special case when alpha is equal to beta. This term is 0, and the population remains constant. So, just one example. if alpha is bigger than beta, so if more animals are being born than are dying, then the growth rate looks like this, and it's just discretized into these individual years or months or whatever it is. Okay. So pretty straightforward. Again, just to reiterate, we always tend to have this term here. So the number of things we have in the next season is going to be the number of things we have now, plus the number that are born, minus the number that die off. And this here is going to be the net growth rate. So net growth rate. And it could either be positive, in which case the population is growing, or negative, in which case the population is decaying. So growing or decaying, depending on that parameter alpha minus beta. Okay, so it's fairly straightforward. It's the same kind of idea as for the differential equations. It's just that these things here, the time intervals are discrete. Okay, so the next thing we're going to talk about are models for interest, so investment basically. So you invest money into a bank and you'll earn interest on your money. Or alternatively, loan repayment. So if you borrow money from someone, and how do you pay it back? So the first model that's it's never used, but it's always introduced, or interest schemes are always introduced like this, is this model of simple interest. So suppose an initial amount called S0 is the principal amount. So suppose this principal amount is invested in the scheme that pays simple interest at P% per annum. Okay, so simple interest is P%, so P over 100 times the principal amount. Okay, and this principal amount we've denoted by S0, so P over 100 is P% times S0. Okay, so basically you put 100 Rand in, and if P is 12%, then at the end of the year you'll get 12 Rand on your 100 Rand investment. Okay, and so how much money will you accrue over the number of years? So the amount of money I have at the end of the next year is going to be the amount I have in the previous year plus P over 100 times S0. And what makes simple interest different to compound interest is that it doesn't compound, meaning that this term here, so the interest you earn, so this is going to be your capital, and this here is interest. So this interest that you earn in a year is only dependent on the initial amount that you put into the investment. So it doesn't consider what the current capital value is. So say you put 100 Rand in 10 years ago, then the capital amount here is going to be much more than 100 Rand, but you're still going to earn interest only on the initial 100 Rand that you put in, not on the current amount of the investment. And that's why simple interest isn't used. And so the solution, so you can solve this first order difference equation, then SK is going to be 1 plus K times P over 100. So we're going to accrue P% of S0 K times, and we're going to get S0 times S0. Okay, so we can evaluate the amount of our investment at any time K. Anyway, moving swiftly along, as I said, simple interest isn't very practical, isn't used, and so compound interest is certainly more common. So compound interest is so it's going to be alpha P on 100 and times the current, so SK is the current capital of your investment. So alpha is the conversion period, so how frequently do you compound the interest. So if, for instance, you compound it monthly, alpha is going to be 1 over 12. Okay, so it's related to what the rate is P. So if P is equal to 1% per annum, and alpha is going to be then the rate with respect to a year. Okay, so with respect to a year, because it's per annum. So if P is equal to 12% per annum, and alpha is equal to 1/12 monthly, then alpha P is just going to be 1% per month. So basically, instead of getting 12% at the end of the year, you get 1% each month. And what this means is, you might think it's this equivalent, but because of this here, because of it taking into account the current amount of your investment, it's better to get 1% per month, because your value will increase every month, as opposed to getting it 12% at the end of the year, because then your value will only increase at the end of the year, and you're essentially getting simple interest within that year. So the more frequently you convert, or the more frequently that your interest compounds, the better it is for you as an investor. And so some investments actually compound monthly or daily, so they are now quite frequent. Okay, so again, this is so the equation that we have is going to be the amount sk plus 1 that we have at the end. So k is now not a year, but our conversion period, so it could be a month or a day, depending on what we decide, is equal to however much we had at the previous time period, plus the compound interest. So it's alpha p on 100. So p per 100 is p% per year, times alpha is the conversion rate, times sk. So we're going to have our current capital plus the interest that we earn on that current capital in the time period alpha. Yeah, and then k obviously goes from 0 to whatever. And again, so it's a first order equation, and we can solve it using techniques we learned in chapter 3. And this is going to be 1 plus alpha p on 100 to the power of k times s0. Okay, so the value, if you invest 100 Rand at 12% per annum compounded monthly, so with these parameters I've given here, then you can tell after k months how much your investment will be worth. And so just to reiterate, that k will represent the investment, the conversion period that's related to alpha. So if I compound monthly, k will then count months. If I compound yearly, then k will count years. If I compound daily, then k will then count days. Okay, so it's important. And as an exercise, if you're interested, you can say, if alpha is 1, what is S1? So what is my investment worth after 1 year? If alpha is 1/12, what is S12? What is my investment worth after 1 year, compounded monthly? And then if alpha is 1/365, what is my investment worth after 1 year in days? Okay, and you should see that these numbers are different, and you can decide which one is it better to do it daily, monthly, or yearly. You can tell me. Okay. So, right, so that's basically if you want to invest money. But now what happens if you want to borrow money? Okay, so the way borrowing works is you tell the bank you want some money, and they say, okay, fine, we'll give you R1 million to buy your house. And you say, great, I'll give you your R1 million back in 20 years' time, or over the next 20 years. And then they say, okay, well, for the cost of you having our money for the next 20 years that we don't have, we are going to charge you interest. And so interest is really just the cost of borrowing money. So just like when you rent a car, you have to pay someone for the usage of their car. Same with borrowing money. If you borrow money, you need to pay interest. It's the cost of borrowing money. So suppose that the compound interest of p% is charged on the outstanding debt of a loan, and suppose the conversion period is equal to the same fraction alpha of the year as the period between repayments. Okay, so if you're compounding your interest monthly, then you'll also make a repayment monthly. Okay, so we let dk be the debt. So dk is how much is outstanding. So if I borrow R1 million, then initially my debt is R1 million. And R is the repayment we make. So if I borrow R1,000,000, then I pay back every month, say, about 13,000 Rand. Okay, so R is the repayment. And what this repayment will do is it'll pay the interest that you've accrued for that month, as well as some of the capital that's outstanding. Okay, so formulation, we say that the debt at the next time period is going to be the debt that you have. Okay, so how much money I owe next month is going to be how much money I owe this month, plus the interest, because remember I owe interest on the amount that I've borrowed, and that interest is the compound interest formula, so alpha p on 100 times dk, so it's the interest on the amount outstanding. So this is the capital this month, the interest that I owe for the use of this money for this month, and then I subtract off R, this repayment that I've made. Okay. And again, first order linear difference equation, you can solve this, and you can then say dk is equal to d naught minus 100R divided by alpha p times 1 plus alpha p on 100 to the power of k plus 100R divided by alpha p. Okay, so it's a first order difference equation, it's non-homogeneous, and so you can use again those techniques that we learned in chapter 3, and it you should get the solution. Okay, so well, what do these look like? What do these repayments look like? So essentially, you can see here the amount that are outstanding. So here is 10,000 Rand, and the amount outstanding slowly diminishes. So it's concave, so it's going that way. So initially, from month 1 to month 2, you don't pay off a lot, but from month say 30 to 31, you pay off a lot more. Okay, and that's because the amount outstanding is a lot less than initially it is, and the proportion of your repayment is it's less interest and more paying off the capital. And then the yellow line is the amount, so you're paying constant amounts. That's how much you've paid back already. So you can see that even after about 40 months, you haven't yet paid the debt off, but you've already paid in more than you initially borrowed. Okay, which isn't unheard of. Okay, so if you buy a house for R1,000,000 Rand, then so this mathematical code, you can again find it in the notes and on Sakai. Basically tells us that the repayment if I borrow R1,000,000 Rand is 13,000 Rand. Okay, so I borrow R1,000,000 Rand, and my repayments every month I have to pay 13,000 Rand, and I pay it off over a period of 20 years. Okay, 20 years, and my interest rate is 15% per annum. Alpha is 1/12, so it's compounded monthly. At the end of 20 years, I've actually paid 3.16 million Rand. So I borrowed 1 million, and I've paid back more than 3 times that. And this is in part because the interest rate is quite high, but also because the term is so long. So when I pay back 13,000 Rand, so much of my money initially, so much of my repayment is just covering the cost of borrowing this money. So just 1 month, so the cost of paying interest on R1,000,000 Rand for 1 month, or the first month, is so very high. So you can see that's what the plots look like. So after 50, sort of 60, 70 months maybe, we've paid R1,000,000 Rand just in. So after about 5 years, we've paid 5 or 6 years. We've paid more than R1,000,000 Rand in our repayments, but we're not even close to paying off our debt. Okay. So as an aside, a kind of interesting observation, you can play around with this code, it's quite interesting. If I double my repayment, so I've got here 2 times 13,000. So instead of paying 13,000 a month, I pay twice that. Okay. Then what happens is I actually pay this off a lot faster. I pay it off in about 4 years and 4 months. So less than 4.5 years, as opposed to 20 years. And what that means is my final repayment, it doesn't say, but it saves me a lot in interest. So rather than paying the 3 million Rand that I paid in interest, I pay a lot less than that. And you can go play with this code and see exactly what it's doing and how much you're saving. But the point is that if you double your repayments, you end up paying the loan off much faster and saving yourself a lot of money on the interest. Okay, so that covers the section on interest and debt repayment, and the next section we're going to talk about is spread of disease and how we can model this using difference equations. Okay, so the next section talking about is models of the spread of disease, and essentially why we might want to use difference equations for modeling the spread of disease is because we wouldn't be measuring how many people are infected with the disease continuously. We would want to measure it maybe once a week or once a month, and then try to gauge from that how quickly the disease is propagating. So section 4.4 of the notes, first model says, in people live on an island, an airborne virus sweeps through the island. Anyone who becomes infected never recovers and death is quick. So that basically means once they're infected, they die. So the number of people infected is proportional to the number alive at the beginning of the previous week. So we let SN is going to be the number of people alive or who are susceptible. And DN is the number of people who have died. Number of people who died. Okay. And so beta is the proportion of susceptible people that die or that contract the disease. Okay. And so if we look at the compartment of this, it's going to have just 2, and people move from the susceptible compartment to the dead compartment. Okay. So the number of people that are susceptible the next month or the next week, the next time period, is going to be the number of people that were susceptible or that are currently susceptible minus the proportion of them that die. Okay, so beta times SN is the proportion of people that die. So beta times SN, so say we have 100 people that are susceptible and beta is 10%, then 10 people will move, so 10% of the 100 people that are currently susceptible will be removed from this compartment and move into the D compartment. And hence the number of people that have died, the number of people that will have died in the next month is the number of people that have currently died, plus the people that die in this period. Okay. So straightforward, we can solve it, we can plot this, and what we see is that as the number of susceptible people decrease, the number of dead people increase, and if I sum these two curves at any point, I get 100. So 0 plus 100 gives me 100. This thing here is 50 plus 50 is 100, and then basically the total number of people in the system is always preserved. Okay. So straightforward model, very simple, not very realistic. Okay. So the next model, model 2, says, suppose it is possible to inoculate people at a rate of alpha people per week, starting immediately when the virus lands on the island. Okay. So we now have 3 compartments. We have susceptible people, we have people that are inoculated, and we have people that have died. Okay. So susceptible people can become inoculated at a rate alpha. So we can't inoculate everyone on the first day, but we can inoculate them over a period of a few days. And then susceptible people can also die at a rate of beta. So once they're inoculated, they're immune and they won't move into the death category. And once they're in the death category, they won't move anywhere else. So the number of susceptible people at the next time step is going to be the number of susceptible people now, minus alpha times SN, so this is the proportion of people that become inoculated, they move into this category, and then minus beta SN, so these people move from the susceptible category into the dead category. So number of people inoculated at time n plus 1 is the number of people that were inoculated last week or this week, plus alpha, so plus the people that move from S to I. And lastly, the number of people that have died by the end of next time period is the number of people that have died this time period plus the number of people that die during this time period. So this term here. So basically this is a number of people that move from S to D. Okay. Once more, it's relatively straightforward. Straightforward model, easy enough to solve. And we can see that the number of susceptible people decreases from 100 down to 0, and then the orange is the number of immune people. So we can see we get about 60% or 60 people immune before they contract the disease and die, and about 40, just less than 40% of the population is not inoculated and die from the disease. Okay. But again, if we add up these three curves at any point in time, the total number of people in the population is conserved. Okay. So, the next model is a little bit more complicated. So it reads that we consider an epidemic where those who get the disease are infectious for 2 weeks and thereafter immune. So you get it's very similar to the flu. You get the flu, you're infectious for a couple of weeks, and then you're immune. Okay. The disease is transmitted by breathing, sneezing, or coughing. A few people die from the disease, but only after complications towards the end of the infectious period. The disease is started by 2 visitors visiting the community of N people. Okay. So again, we have S for the number of susceptible people. So I'm going to draw the compartment first. So we have number of susceptible people, and N. So I'm going to have little n is going to represent weeks. Okay. And what I'm going to do is, because they're infectious for 2 weeks, what I'm going to do is I'm going to represent them as 2 separate blocks. So this is going to be infectious, the first week of infectiousness and the second week of infectiousness. Okay. So when you're susceptible and you get infected, you become infectious in the first week. After 1 week, you move from F1 to F2 in the second week of infectiousness. After the second week, you become immune or die. So M for immune and D for if you die. Okay. So if you're susceptible, you can only become infectious. Okay, you can't jump from being susceptible to immune. Once you're infected, you can only move to F2. So if you're infected in the first week, you can only move into the infectiousness of the second week, because the problem states that people who die from the disease only do so because of complications late in the infection. So a small proportion of them will die, and we call this beta. And then a much larger proportion, called as lambda, equals 0.999. This is going to be 0.0001. So 99.9% of people then become immune. Okay. So what we do is consider number of susceptible people first. So number of susceptible people at the next time step is going to be the number of susceptible people that we currently have, right, minus the people that become infected. So I'll call this, what have I called this? Call this K1, K2. So the number of people that move from S to F1 is going to be K1 Sn times F1n. Okay. So you might be asking now, why do I multiply Sn by F1n? Okay, and this is to represent there's an interaction that's happening here. So the people that are infectious must infect the susceptible people. Okay, and so if there were 0 infectious people and we only had this term, it wouldn't make sense that people would still become infected. So if F1n was 0, then there would be no one to infect the susceptible people, and it wouldn't make sense that this term still took people out of the susceptible category. And in fact, there are 2 different kinds of people. So the first week infectious and the second week infectious can both infect the susceptible people, and so we need that. So if there are 0 people in the first week of infectiousness and 0 people in the second week of infectiousness, then this whole term should be 0 and no one should move from S to F. Similarly, if there are no susceptible people but there are infectious people, there shouldn't be anyone moving. So this whole term should be 0, and then Sn should remain constant. Okay. So from a modeling perspective, we go back to that term that I used in the first few chapters, a sanity check. So we do a sanity check. Does it make sense? If there are no people in the susceptible category, should people be moving? No, they shouldn't. So this is going to remain 0. If there are no infectious people, should people become infected? No. So F1 and F2, if those are 0, this whole term 0, and Sn plus 1 is equal to Sn. So the susceptible population remains constant. Okay. The number of infectious people at time n plus 1 in the first week of infectiousness is going to be the number of people that are there at this time step, minus all of them. Okay? And then plus, so this is basically people that are infectious in the first week, and because a week has passed, they move to the second week, plus the people that come in is going to be K1 Sn times F1n. So this term here is going to balance with this term here. Okay? Similarly for F2n plus 1 is going to be equal to the number of people that were currently in this. Okay? Plus the people that come in, so it's going to be the people in F1n. Alright, so this one. So you don't need K2 can be 1. And so the people that come in is this here. The people that then leave is sorry, so this term here should be F1 plus F2n, right? Because the susceptible people can't jump the first week of infectiousness. Okay, so the people that move into the first week of infectiousness is going to be, well, the number of people that are infected in the first week of infectiousness are the number of people that were there minus people that leave. So because they're only there for 1 week, they must leave, plus everyone that leaves the susceptible category. So if they become infected, they can't move into this category. They have to move into the first category, and that's represented by this term. So this term here matches with this term here. So the second week of infectiousness is the number of people that were there last week, plus the number of people that came in from F1 that survived a week and moved into there, minus the people that become immune. That's lambda F2n. So lambda, 99.9% of these people move to M, and beta times F2n move into D. Okay, and there's no interaction between these populations, so that's why I don't multiply these two things. So even if there were no immune people, people will still become immune. Okay. And then finally, or penultimately, Mn plus 1, so the number of immune people at the next time step is equal to the number of immune people now, plus these people here. They become immune, lambda F2n. And lastly, the number of people that have died, n plus 1, is equal to the number of people that have died in the previous time step, plus these people here, beta F2n. Okay, and you can see if I add up all these terms, everything should cancel off and I get 0, because the number of people in the system should be conserved. Okay, so no one's being born, no one's dying naturally in the immune thing, so the system is contained. So everyone's conserved. So what does the solution look like? So blue here is again the susceptible curve. You see that some people, okay, so the blue is susceptible. I'll come back to that other point. This red or dark orange color is the number of people that are immune. Green is the small proportion of people that have died. And then this little peak here in yellow is the infectious people. Okay, so F1 plus F2. And you can see that in the first 2 weeks or so, first 7 days to 10 days, there's a spike in infectiousness. So lots of people become infected. And that's when the death rate rises. So proportionally a lot of people die in that period. But lots of people become immune as well. And so you can see here the blue curve, the number of susceptible people, doesn't actually reach 0. And so what that means is there are about 10 lucky people that completely miss the infectious period. Okay, they're lucky enough not to interact with someone that's infected, and they remain susceptible for the whole period, and they actually get to the end where there are no more infectious people, and everyone's either immune, dead, or still susceptible, but because there are no infectious people, these people can't then get sick. So it's actually quite realistic. You see people in the winter months, lots of people get flu, this yellow curve here, lots of people get infected, lots of people become immune, but there are always those lucky few that actually never get sick. And then what I've done here just below is I've added up for every time step, every time slice in this picture, I've added up all these numbers. You see I've got 102 for all of them, 102, 102. And what that is the 100 people in the population and 2 people that are infected that are initially put into that population. And that's what kind of kickstarts the whole process. But for every time step, the number of people in the whole system, so the number of people that are susceptible, infectious, that have died or become immune, is all constant if I add them all up. Okay, so no one's coming in and no one's leaving. Okay. So hopefully that makes a bit of sense. I know the model becomes quite complicated quite quickly, but it's quite a realistic representation of what's actually happening. So the next section is Fibonacci sequences. So Fibonacci, or Leonardo of Pisa, was a 13th century Italian mathematician, and he kind of proposed this idea. So it says here, we look at the case, so a newly born pair of rabbits, so we have a pair of rabbits, okay, and after 2 months the rabbits will become adults and they will then reproduce, so they'll produce offspring, a pair of rabbits. So we have young rabbits initially, and it's one pair of rabbits, so it's not one rabbit but one pair of rabbits, and O for old rabbits is going to be 0, so we have 0 old rabbits. Okay. We then say the number of old rabbits at the next time step is going to be equal to the number of old rabbits we had. So another one of the assumptions of the model is that the rabbits never die, and it's obviously not very realistic, but it's just an indication. Well, it's just a mathematical curiosity. How would rabbits grow if they didn't? Okay. And this Fibonacci sequence is actually very famous, and we'll see why in a bit. So the number of old rabbits the next time step is equal to the number of old rabbits we had, plus the number of young rabbits. So these young rabbits will become old, and the number of old rabbits will increase. Okay. The number of young rabbits at the next time step will be equal to the number of old rabbits at the current time step, because these old rabbits will reproduce. Okay. So the old rabbits at the current time step will produce one pair of young rabbits at the next time step. Okay. So old rabbits in the next time step is equal to the number of old rabbits now plus the number of young rabbits, because these ones will get old, and the number of young rabbits in the next time step is equal to the current number of old rabbits, because every one of these pairs will reproduce and produce one pair of young rabbits there. Okay. So I can combine these two things and say that, so this expression here I can rewrite as yn equals old n minus 1. So just by shifting the n index, I can then substitute this back into this equation, and I get old n plus 1 equals old n plus old n minus 1. Okay? And just to use the notation in the notes, fn plus 1 is equal to fn plus fn minus 1. Okay. And this describes the Fibonacci sequence. I know from these conditions here at the top, I know that f0 is going to be equal to 1, and f1 is equal to 0. Okay? So you can just check those. And then I can then say, well, f2 is equal to f1 plus f0 equal to 0 plus 1. That's just 1. f3 is equal to f2 plus f1 equals, so f2 is 1, f1 is 0, it's 1. f4 is equal to f3 plus f2 is equal to f3 is 1, f2 is 1, 1 plus 1 is 2, and then get the sequence 1, 1, 2, next one's 3, 5, 8. and so on and so forth. So you can go and check them. This is a Fibonacci sequence. Okay. And what's really interesting about the Fibonacci sequence is that if we take the limit as n tends to infinity of fn plus 1 on fn, so the proportion of successive elements in the series, this limits to 1 plus root 5 on 2. And this thing here is called the golden ratio. And you'll see that this golden ratio comes up, if you Google it, it comes up in a lot of different aspects in nature, in art, in architecture, these kinds of things. So as an exercise, what I want you to do is prove this, right? And I'll give you a couple of hints. The first hint you need to do is consider xn be equal to fn plus 1 on fn. Right, so you're going to consider the limit as n tends to infinity of xn. Right, and you want to try and prove that this limits to this number here. The next hint I'm going to give you, so we have that, and I think that's all you need. Yeah, that's all you need, and a bit of thinking, and you should be okay. Okay, so hopefully that makes sense. And there's one last model on page 12, top of page 12, where they just consider different initial conditions. They consider 1 and 2, and you can go through it, but you get the same sequence, same series, so it's not terribly important. And then chapter 4.6 on supply and demand is not examinable. Okay, so I'm not going to talk about it. If you're interested, you can look at, there's a textbook on Sakai by a guy called Jacek Bazniak. He's a lecturer at UKZN, and it's on Sakai. It's called J. Bazniak Mathematical Modeling, I believe. In PDF form, it's free to download, it's free for you to use. And if you're interested in the supply and demand stuff and mathematical economic stuff, feel free to read through his book. He puts together a very compelling set of equations and a good argument. So yeah, so it's called jbazniakbook.pdf. So go ahead, and I encourage you to read that if you're interested in that. But the notes, I don't think appropriately capture this, so I'm not going to talk about it at this stage. Okay, so hopefully that makes sense. That's the end of chapter 4. It's the end of the course. And if you have any questions, as always, feel free to direct message me on Twitter, on YouTube, on email, anything like that. Thank you.